All right, today we are talking about 5-4. I just recorded this whole section and my volume wasn't on, so it had no sound. So this is take 2 all the way through. Here we go. There's 3 sections to this, 3 parts to this section. The first is how to find the average value of a function. And each section has its own theorem. All right, so here's the average value theorem. If f is continuous on a closed interval, then there is at least one point C in that interval, in that AB interval, such that f of c equals 1 over b minus a with the integral from a to b of f of x dx. Okay, so a couple things. First of all, f is continuous on AB. That's a requirement because the proof of this theorem involves the extreme value theorem, which also requires that f is continuous. Okay, and if you think about it, if we're talking about the average value of a function, like where is it roughly most, or where's the middle, sort of, so to speak, it makes sense that the function would have to be continuous. If it has a break, it might actually miss that middle value. So that's the idea there. And this is really the nuts and bolts of the theorem. This is the formula, so to speak, that you will be using. B minus A are the bounds of the interval. This guy right here, your start and finish of the interval. And let's look at what a real nuts and bolts problem looks like. It'll say, find the average value of a function, let's say x over 2, on the closed interval from 0 to 6. Right? So you're going to pull out your formula, f of c. This is your average value formula. And we're going to start plugging in some values. All right, so the function evaluated at c is x over 2. And b is 6. And a is 0. And again, right here, that doesn't look like a 6. That looks like a b, sorry. Okay, and then b up here is 6, and a is 0. And the function is x over 2 dx. So that fills that in. Oh, by the way, the proof of this, if you are interested in where this came from, is on page 541. You can take a look at that if that interests you. All right, so let's figure this out. This is the area under the curve, right? So I think because this is a line, it might be easier to figure this out with geometry. It's a line that has a y-intercept of 0 and a slope of 1/2. So it's looking like this, roughly, okay? And we're going from 0 to 6. So I want this area right here. Well, since that's a line, the area is just a triangle. So the area of that red region is going to be 1/2 base times height. So that's going to be 1/2. The base is 6 and the height is 3. I didn't draw that to scale. You use your imagination. It should go up to 3. And so my area here is going to be 9. So that's what this value is. So I get 1/6 times 9, which is going to be 3/2. Now, oh, sorry, this is a typo right here. This is f of c. So that means I need to plug in c up here, not x. This is a specific value that I'm looking for. Where is that average value? Now, if the question asks, what is the average value? This is your answer, okay? The right-hand side of the function is the average value. But if the question asks, where does this occur? Then whenever I ask about where, I'm asking about x values. And that's going to be your c value. So if I want to know where is this going to happen, I'm going to solve this for c. So I go ahead and cross multiply. 2c equals 6. Divide by 2 and c equals 3. So this is where it happens. So you might write a sentence like this. The average value is 3/2 and it occurs at x equals 3. So let's look at the picture. Here's 3 midway right here. The average value is 1.5 right there. And it makes sense. 3's in the middle. It's a line. It's not doing anything weird. It should be right in the middle. There will be problems that aren't lines and they're curvy, and so the geometric understanding of them might not be as clear as it is on this, but the math will be the same. So you can try a couple of these. Example 5.15 is a good one to try, and if you want another one, 5.16 is also one of these types of problems. So you can pause and try one of those. All right, next is the fundamental theorem of calculus, part 1. There are 2 parts to it. I wrote 2 when I said 2, but it's part 1. All right, here's what it says. If f is continuous, we always like it to be continuous. That's why we spent time in the beginning talking about continuity, because so many of these theorems depend on that. Over an interval AB, closed interval, and capital F we're going to define is defined by being the area under this specific curve from a to x, f of t dt. Okay, that's how we're going to define that. Capital F is the area under the curve between a and x. Then what we know from this theorem is that if I take the derivative of both sides, I just get the function evaluated at x. All right, so basically what this is saying in English, it's a lot of fancy math, but it's saying if you take the derivative of an integral, they cancel each other out. That's kind of the heart of what it is. Now there's a few specifics. First of all, the fact that this is an x right here is very important, and it has to look exactly like this. This has to be an x. And what this is a specific place at the function. So this whole area is still going to be a number. It's just dictated by where you are. This is your x value. Where are we? Okay. And a has to be a number. It's a constant that doesn't move. Okay. It's on your boundary. And it has to be in this order. The x has to be on the top and the number has to be on the bottom for this to work. And what happens is that if you take the derivative, so what we're saying is if you take the derivative of each side of this equation, that's what this is, then these guys cancel out basically, and it's just the function wherever you are evaluated at x. Okay? So what we're gearing up to say is that the derivative and the integral cancel each other. They are inverse functions. Okay? Let's look at an example. This is a really straightforward example. We'll get a little complicated in a second. Okay, so we're going to define G as this area under the curve, and I want you to find G prime of x. So basically what I'm saying is I want you to take this function and I want you to take the derivative of each side. When I take a derivative of the left, this is g prime of x. That's what I'm looking for. And over here, because I've got an x on top and a number on the bottom, okay, a boundary line, then this derivative and integral cancel each other out, and I just get the function evaluated at my x value, wherever that may be. This is the answer. That's it. Okay, let's do one that's a little bit more complicated. What if the top isn't an x? What if it's something more complicated? All right. This can still work. It's just that I have to make this be a single variable. So what I'm going to do is I'm going to make a substitution. I'm going to say let u equal the square root of x. Oftentimes in calculus, when we're going to make a substitution, we use u as the letter. You don't have to use u. You can use something else, but that is what I will continue to use. Now, what's going to happen in this is we're going to take, directions say find f prime of x. So what that means is we're going to take the derivative of both sides of this. Now, remember when we were doing derivatives, everything's a chain rule, right? Well, no different here. This is actually a chain rule. This is the outside function, and this is the inside function. So what's going to end up happening, because we're taking the derivative, we are going to want to know what the derivative of this u value is. And I'll show you where that comes in a minute, but we're going to calculate that. So the derivative of the square root of x is 1/2 x to the negative 1/2. Okay, that's what du dx is. And now we're going to substitute that in. So I've got f of x now is going to be defined as 1 to u sine t dt. And now when I go and take the derivative of both sides to find the thing I'm looking for, I get f prime of x equals, now watch, derivative of the outside function, sine, okay, evaluated at the inside function times the derivative of the inside function. Now, why the reason that I didn't actually take the derivative of the sine is because this derivative and the integral cancel each other out, but I still have to kind of finish that chain rule, if you will, right here. So these cancel, and the sine gets to stay what it is, but I still have to evaluate at the inside function times the derivative of the inside function, right? And so that ends up being, then you can substitute back in. So u is going to be the square root of x, and du is going to be this 1/2 x to the negative 1/2. So if you want, you can write that as sine root x over 2 root x, and that's your answer. Now, this whole thing, this du dx thing, is technically happening up in here too. It's the derivative of the outside function doesn't change because the derivative and the integral cancel, so it's right here, evaluated at the inside function times the derivative of the inside function. Well, the inside function's x and the derivative of x is 1. So that's why we don't, it's kind of like, it's what we've been going through all along, okay? Where the derivative of the inside function is 1 at the beginning, but then later as we progress, it gets more complicated. Okay. Let's do another one of these. Right, another example. We're going to define f of x as the integral from x to 2x of t cubed dt. And same directions, we want you to find f prime of x. Now, this has two issues. The first is the same as last time. This is not a single variable. But the other issue is that this is not a number. I mean, not a constant. Okay, x changes depending on where you are. So we need to fix that. If you go back to our properties of integrals, I give you a page number to look those up. One of the things that you can do with an integral is you can break it up at any point along the way. So for example, if you have a function like this, and you want to find the integral between here and here, well, you can find the whole area all at once, or you could break it up, and you can break it up anywhere you want. You could break it up here, let's say at 0, and find the area of that piece right there, and then you can add that to the area of the rest. And if you add those up, that equals the same area as the whole distance. That's the idea that we're going to use here. I've got this area from somewhere, just to put a visual on it, let's say like from x to 2x, you know, wherever those might be. And what we're going to do is break it up somewhere in the middle. It doesn't have to be, it doesn't matter where you break it up, as long as this is a constant number. So what I'm going to do, typically we just break it at 0. So I'm going to say, I'm going to go from my left bound x to 0 of the function, and then I'm going to add that to 0 to 2x of the function. All right. Now I fixed the issue that I don't have numbers involved. I do. Now I have numbers. The problem here is that it's on the top, and I want it on the bottom. So one of your other properties says, hey, you can switch these orders. You can take the 0 and switch the order with the x. You just have to change the sign in front. Okay, it changes the direction you're measuring, and so it changes the sign. So this is going to be negative 0 to x. So that fixes that problem. Now over here, I have a different problem. The 0 is in the correct place, but I've got the same issue that I had in the previous problem, which is that this needs to have a single variable on the top. So I'm going to let u equal 2x, du dx is going to equal 2, and I'm going to make that substitution. So this guy doesn't need a substitution, it's good to go, but this side I'm going to tell it to go from 0 to u t cubed dt, and now I'm going to take the derivative of each side. So f prime of x, derivative of the left, is, now what happens? The negative comes down along for the ride always. The derivative cancels with this integral, and it says evaluate the outside function, which is t cubed, evaluated at the inside function. Okay, so that means I'm plugging in x times the derivative of the inside function, but the derivative of x is 1. So that's it. That's this guy. Plus, now here, derivative of the outside function stays the same because the derivative cancels with the integral, but I evaluate it at the inside function. So this becomes u cubed times the derivative of the inside function. Okay, I can substitute that stuff in, and I'm going to get u is 2x cubed, du is 2, and so this ends up being negative x cubed, and this is going to be 16x cubed, so my answer is going to be 15x cubed. So what this does is it gives us a way to figure out what f prime of x is. It's going to be 15 times the cube of wherever you are, whatever your x value is. So you tell me where on the picture you want to be, and I can give you a number value. That's the idea. Okay, try a couple of these. Section 5.18, the check your understanding problem, and the 5.17, the check your understanding at the end of the examples. The solutions are in the back of the book. And lastly, let's do the fundamental theorem of calculus, part 2. All right, if f is continuous, over the interval a to b. And we're going to define capital X as any antiderivative. Now, but I'm going to pause here for a second. This is hearkening back to 4-10, okay? Antiderivatives, remember, we defined with capital F of X, and the reason it says any antiderivative, remember when we were doing antiderivatives, like say this guy, the antiderivative is going to be x cubed over 3, but we said, hey, you could have a number over here, so we put a plus c, right? Because the derivative of the c gives you back 0, and so it doesn't really matter. So this is what it means by any antiderivative. It means this c value can be anything, all right? So that's how we're defining capital F. Then we are going to define, we've defined this integral. This was our Riemann sum. Remember that? Okay, so this is the Riemann sum, the limit of the sum as n goes to infinity of all of those squares. Turns out that this equals the antiderivative evaluated at b minus the antiderivative evaluated at a. So what this does is it says, hey, guess what? Those 5-1, 5-2 problems that were such a pain in the butt, they're actually equal to 4-10 problems where all you have to do is do the antiderivative, which wasn't very hard. You just raise the power divide, right? And all you got to do is plug in the n values. Ta-da! So here's the good news. With this theorem, you don't have to do all of those summations anymore. You don't have to do the rectangles, you don't have to do the limits, and they were so complicated. So this is a huge deal that now we have this shortcut, so to speak. It's kind of like with the derivative, that definition with the limit and all that was such a big pain. And then we said, hey, by the way, here's the shortcut, here's the connection, and this is the same idea. So what this is saying in English is, guess what? The antiderivative is the integral. Yay. All right. So what we're going to do is we're going to live here for the rest of the course and say, how do we calculate these? What are some techniques? All right. So let's start at the beginning with something that's just kind of straightforward. Okay. So here's a function. I want you to find what this is saying is find the area under this curve between -2 and 2. I'm going to draw you a picture just for fun because I think that sometimes helps to connect, but you don't have to draw the picture. Just want to show you this is a parabola that is shifted down 4 if you remember your pre-calculus. And I want to find the area under the curve between -2, all right, so here, and, I don't know, well, it's not to scale, let's just it's a sketch, okay, between -2 and +2. So remember we talked about how the area above the curve is positive, below the curve is negative, and before we would have had to create a bunch of rectangles or do our summation formula for this, and it would have been a long process. But now we say, hey, all I have to do is find the antiderivative of this, so let's do that. This is going to be t cubed over 3, raise the power by 1, divide by the number, minus, now this power is technically 0, so I'm going to raise the power to 1 and divide by 1, all right? And I'm going to evaluate that, and here's the notation. We put a straight line at the end, evaluate that from -2 to 2. What this means is, here's my boundaries, but I haven't plugged them in yet, okay? And now I'm going to plug them in. So it says take f of b, this top boundary first, 2 cubed, and plug it into your function. This is my f of b. And then minus my f of a. So take your lower bound and plug it in. And then calculate that. And if you do some math out, this ends up being negative 32 over 3. So this right here is the area of the red region. Bigger amount of area under the curve. That's why it's negative. That's what that means, is there's more stuff down here than there is up here. And if I had drawn a little more carefully, you can almost see that that's true here. But if you draw it really carefully to scale, you'll see that there's just a smidge of red in these upper areas. So it's much bigger amount of area down below. Okay, so sometimes you can kind of look at these numbers and see if they make sense, which helps catch mistakes sometimes. Okay, now, what happened to the C? Because remember when we did these antiderivatives, I'm going to do this in green. This is not really part of the problem. I just want you to see this. Technically, there's a C here, right? Okay, well, let's put that in. So here's f of b. I should have a C here. And f of a, I should have a C here. But what happens is this negative distributes in and makes that a negative C, and this is a positive C. So these guys always cancel each other out. And that is why the theorem works for any antiderivative, because it doesn't matter what that C value is, it's going to get canceled out in the subtraction every time. So two things are going to happen. One is I could ask you for what is a general integral. Then you're going to add the C on there, like the general antiderivative. But if I ask you for specifics where you're plugging in numbers, the C values cancel. You don't need them. All right, you can try one of these. Try example 5.19, the check your understanding problem. And I'm going to do one more for you to look at. So let's do the integral from 1 to 9. Square root of x dx. Remember back in 410, there is no product or quotient rule for antiderivatives. Now, there will be other techniques coming, but for now, we have no skills, okay? All we can do is term by term. So if you have a quotient, like I'm looking at right here, you've got to break this up algebraically somehow. Now, if you're going to do something algebraically, this integral sign needs to stay on. It stays on until you take the antiderivative of the function. So I'm going to first break this up into two fractions. Okay, the thing I want you to notice here is every time I do that, this dx is staying on there as well. The dx stays on until you take the antiderivative. And if you've got subtraction in your function, you have to have parentheses around the whole thing. It's just like the logs and the sine. It's like that locked box that you have to have in parentheses every time. All right, so I'm going to do one more algebra step. So I'm keeping the integral on. I'm going to call this x to the 1/2, reducing that power. And this is, I'm going to bring this up top and call it negative 1/2. So now I'm going to take the antiderivative. So I drop the integral sign. This increases by 1. 1/2 plus 1 is 3/2. And I divide by that number. Minus negative 1/2 plus 1 is 1/2. Divide by 1/2. Straight line, 1 to 9. That means I haven't plugged in my numbers yet. I've only taken the antiderivative. I'm going to mark you off for notation on the homework quiz, so make sure that you are clear on when you drop things and when you plug in. Okay? Now I'm going to plug this value in. So this is going to be 9 to the 3/2 minus 2, 9 to the 1/2. This is my f of b minus f of a. And you can do some calculations on those. I think it ends up being 40 over 3. Now, use your calculator as a tool at this point. it has value for you to graph this function and look at it between 1 and 9. And it should be a positive area, should be above the x-axis mostly. And just kind of see if your answer makes sense. All right, that's this section. Good luck and work some problems.